And I had OBS set to record the wrong thing. So sorry about that. We just don't have a copy of the audio from last week. So mea culpa. Um, I'm behind on making videos. I owe you a solution video to Wednesday's recitation. I also owe you a solution video to the homework that you just turned in. I will make those hopefully this afternoon as soon as I get to them. Um, it takes a long time for me to do the recording, especially when I like screw up the algebra in something or make a mistake or forget to turn my mic on and have to redo it. So I will get you those as soon as I can. Um, I've gotten a ton of mail about exam three. Um, People have said, I don't have a grade. I got a low grade. Can you tell me why? I got a low grade. Can you regrade it for me? Often the answer is the reason you got a low grade is because you messed up the physics. But there's a lot of these emails. There's only one of me. I'm working through them as fast as I can. So I'm sorry that's taken a bit. Um, a few announcements. There is a short homework 14 that's due next Thursday. It will be either 4 or 5 problems. We will post it likely in a couple of hours. We're polishing up just a little bit of collaboration between myself and Professor Rudolph in getting it written. We have clinic hours coming up. Our standard hours on Friday. I'm going to have a ton of clinic hours next week, which I will tell you about in a moment. You have papers coming up. Those are due next Friday, so a week from tomorrow. Um, there's going to be a Blackboard submission link for you all to click on and submit stuff to. Are there any questions that you have about your papers? While you're typing your questions, I'd like to talk about a few frequently asked questions. The first one is, no, you don't have to write about a single claim by a single person. You may write about a broader movement. Some examples you could write about flat eartherism, modern flat eartherism in general. You don't just have to talk about one stupid thing that Kyrie Irving said on Twitter. I'm assuming he talks about this on Twitter. Twitter seems to be where like stupid comments go these days. Um, you could talk about like a broad coherent movement. You don't have to talk about things that professional scientists say. You could talk about any claim made by anybody. Um, these could be politicians, these could be washed up basketball players, these could be um, people of any stripe. These could even be things that are commonly believed. The idea that you can record ghosts on a tape recorder. Um, but your claim does need to be scientific. And I'll get to your questions in a moment. Um, this is not a paper where you pick some religious claim that you disagree with and tear it apart. Uh, this is not a claim where you take things that people not well in touch with reality have said that are just kind of nutty. Um, this is, we want something where somebody has said something that's not well founded, but it has the veneer of being well founded because it appears to be conducted using the scientific method. So, um, and broadly defined. So, we've had people write amazing papers about the science of political polling. We've had people write about fad diets, things that um, aren't like part of a science class, but that still are purport to be based on data and empiricism and stuff like that. Um, Okay, questions from folks. Matthew, you never got feedback on if your topic is good. Why don't you type your topic in chat right now and I'll give you some feedback. Jonathan, yes, you can change your topic. Tammy, we're focused on teaching right now rather than like accounting. As soon as we are all not teaching anymore, we will take care of that. We're gonna have to. We have all the logs. We've just got to go back and do it all. Derek, I don't know if you want to send me an email asking about your homework grading. I can take a look. Um, I can't say for sure without knowing who your TA is and like seeing your assignment, but if you want me to take a look at it, let me know. And Matthew, just type your topic in chat. Matthew, that's a fantastic topic. Um, Vincent, your exam three grade. Did you send me your exam three by some like? Was it sent to me directly by email? Yeah, I am buried by mail. Don't worry, you will get your grade. I'm just working through my email as quickly as I can. But it takes time to like make slides and make solution videos and stuff like that. So, grading kind of gets slowed down because I want to make sure that we have class. I'm also covering another class for a professor who has been very sick. So I'm like teaching a class that's not even mine right now and kind of having to figure out what's going on there. And that's taking extra time. Um, so yeah, Matthew, that's a great tie. Fad tie-ups are a great topic. Um, Emily, if you want comments, so that your homework grader may not have sent you comments. If you want comments, send me an email or a message on Discord, and I will just tell me what your topic is, and I'll give you my comments. Um, Andy, if you could send me an email and tell me that your TA is Prashali and what you have graded, I will take a look and I will talk to Prashali. All of the TAs, they're a couple weeks behind. It takes longer to grade online homework um, because remember, so she is a first year PhD student. She has exams next week as well. So she's having to scramble to make sure she passes her classes. Not that she'll have any trouble because she's very good at physics, but um, grading is going as quickly as possible. But if anybody's like more than 2 or 3 weeks behind, then let me know and I'll talk to them. Thanks, Andy. Just shoot me a note and I'll get that taken care of. Any other questions about papers or anything else about the class? The next slide is our schedule. So, actually, no, the slide after that. So if you're looking for help with your papers, if you want someone to read a draft, email any of us. So Nori and Julian are coaches, and Mario is a GTA. And they're probably the best ones to give you advice. We're not going to be able to like tell you what your grade would be, but we can definitely give you feedback on your paper and give you advice for improving it. Remember, the grades for your papers can go above 10. Truly exceptional work will get over 100%. So yeah, Jonathan and Andy, like if any of your TAs are more than 3 weeks behind on homework grading, send me mail and I'll get that taken care of. Other than Vidyesh, I know that Vidyesh is way behind and we are working with him to get him caught up. So you don't have to tell me that Vidyesh is behind. So schedule for finishing up the semester. Later today, we will post your last homework set. Samantha, your final will be at least 24 hours. It may be longer than 24 hours. I'll talk about the final now. The final will be a little bit longer than exam 3. So rather than 4 or 5 questions, it may be 7 or 8 questions, 6 or 7 questions. We anticipate that a well-prepared student will take between 1.5 and 2 hours to do the final. We anticipate that a student who needs to go back and like look at a bunch of YouTube videos and basically relearn a bunch of material may take 3 or 4 hours to do the final. That's if you've got to dig over like all of our notes. But we do not anticipate that the final will take anyone longer than 4 hours, even if you have to do a ton of review. The final will be posted at 3 p.m. May the 4th. It will be due no earlier than 3 p.m. May the 5th. We may give you more than 24 hours. I'm still working with Professor Rudolph on that. Some component of your final will be multiple choice. It will either be true, false, or sometimes, always, never, or positive, negative, 0, or something like that. This is so we can get you your grades more quickly because grading takes a lot of time on our end. And the final is comprehensive. It will go back to, or cumulative. It'll go back to the beginning of the semester. So here's what's coming down the pipe later in the semester. So homework 14 goes live later today. Friday is the last recitation. You really ought to go. Hint, hint, wink, wink, nudge, nudge. Friday, there are also clinic hours. I didn't mention them here. So I'll be in the clinic from 9:30 to 11:30. Professor Rudolph will be in the clinic from 1 to 3, Syracuse time. Next Tuesday is our last day of lecture. I'll be in the clinic from 3 to 5. Wednesday, I've got help hours. That's primarily going to be to help people with homework, but we can talk about anything else too. And then I'm going to be holding a ton of review sessions. Thursday, Friday, Saturday of next week. These are all intended to help people study for the final. Please bring your questions. If there's anything in the previous part of the semester that you weren't quite clear on, if there's just some exam problem that you botched, you get another chance. So bring that exam problem, tell me what it is, and we will review it. You know, many of you told me that the review before exam 3 was very helpful. I hope that these will be helpful as well. Saturday, I'm going to be holding a late night review session, 8 to 11 p.m. This is here to accommodate people in East Asian time zones. So are the help hours next Wednesday. Monday, May the 4th is your exam. Papers are due next Friday. And your homework is due next Thursday. Any questions about our schedule for the end of the term? All right. So today I'd like to take a look back. I'd like to review our previous homework set and possibly the recitation you did yesterday. I have 2 sample problems that we're going to do. And then I want to talk about how torque and conservation of energy link together and talk about basically the rotational work energy theorem. So that's what's coming. Are there any questions about homework 13? So a bunch of students were saying, hey, I'm not so sure about something. So I decided that anybody who is here in class may have an extension until the end of day today if you want to revise your submission. So if there's like something you didn't understand in homework 13, you think you may have not done one of the problems correctly, ask now, and then you can fix it and turn it in by the end of the day. I'll give you all a moment to think back over homework 13. If anybody is looking for the link, homework 13 is right here. I just posted in chat. Can you do the last problem? Yes, we can. So here is problem number 5. So that problem asked you to imagine a satellite in an elliptical orbit. So here is an elliptical orbit. Notice it's not quite circular. And there's Earth. Maybe it shouldn't be dotted. There we go. That's not exactly where the focus is. It's closer to there. Yes, we can do 1A as well. And number 3, Renji and Jasmine. So in this problem, this satellite orbits. We'll just pretend it's clockwise for now. And we have told you the closest distance and the furthest distance. So you can do that just by observing the orbit. So this distance here, you know. This point here is called perigee. And the radius at perigee is known. this point, called apogee, the furthest from Earth, you know both the radius and the velocity. And the problem asks you to find the velocity at perigee. And just so I have room to write, I'll put that up top. RP known, we want the velocity at perigee. So we've talked about multiple techniques for solving these sorts of problems, right? We've talked about, well, what are they? What are all of the techniques we've used to analyze rotational motion? There are three main ones. Conservation of energy. What else? Angular momentum. And torque, and maybe along with kinematics, if we're interested in changes in velocity or time or something like that. Yeah. So this is torque equals I alpha. So of these three techniques, which ones what do we need in order to use these techniques? So there's certain, let's go in order. In order to use conservation of energy, I need clear before and after pictures. Well, we'll write this over here. So to use energy, I need clear before and after pictures and the ability to account for the work done by all forces. Yeah, so Gabriel just wrote down the equation for angular momentum. For angular momentum, I need, and we're going to come back to this checklist for problem 3 as well. That's why I'm spending time on this. So what we're writing down here is kind of broadly useful. I need also clear before and after pictures. My program just crashed. Give me one moment to get it back. There is some crash bug that's still in Cernal, which is the program that I'm using for this. One moment. Thankfully, it autosaves. But it switched to red when I loaded. There we go. So I need clear before and after pictures. I need angular momentum to be conserved. So what must be true for angular momentum to be conserved? Well, I need no external torques. So angular momentum is conserved in the first place. And then finally, for rotational, well, we'll write it this way. For torque equals I alpha and rotational kinematics, I need alpha to be constant. Otherwise, math is hard, because then we can't use our kinematics formulas. I apologize for my sloppy handwriting here. I was over on the edge of my tablet where it's difficult to write neatly. So let's think about which of these criteria apply to this problem. So we've got before and after pictures. We'll come back to work. Are there any external torques in this problem? No. Yeah, because no matter where the satellite or planet or whatever object it is here, right, the force of gravity points directly inward and thus doesn't apply a torque. So, and this is the big one, angular momentum is conserved. So you can use conservation of angular momentum in this problem. Alpha is not going to be constant here. So using rotational kinematics doesn't work well. Now, I want to talk about the ability to account for the work done by all forces. Because some of you may be saying, oh, well, why don't I use conservation of energy here? Isn't energy conserved? Didn't we have a problem on a practice exam about this? You did. Let's talk about how you could use conservation of energy. To be clear, angular momentum is how we expected you to do this problem when we wrote it. But you can use conservation of energy as well. And actually, anybody who uses both methods and compares the answers might get extra credit. I'm going to tell the TAs to look for that. So let's talk about that. I need one extra page to write on. So in number 3, remember, you have the Earth and you have an elliptical orbit around it, right? So the problem here, you might think that, oh, well, shouldn't it be simple to write something like kinetic energy at aphelion plus potential energy at aphelion equals kinetic energy at perihelion plus potential energy at perihelion. Right? Can't I do that? But the problem is that the potential energy here is not just mgh, since we're in space, and the force of gravity is not just mg. Right? Instead, the force of gravity changes with distance. So you need a new formula for potential energy due to gravity in space. And it turns out that that potential energy is minus gmm over r. Notice the minus sign out front. Notice the single power of r in the denominator. If anybody is wondering where that comes from, remember that, whoops, that tool, remember that work is the integral of force over distance. So that's the integral of gmm over r squared dr. But if I rewrite this to make it clearer, that's going to be gmm times the integral of r to the minus 2. And the integral of r to the minus 2 is just minus r to the minus 1, for those who are in Calculus 2 who have done that. So the work done by gravity, which is the same as the gravitational potential energy, is gmm times minus r to the minus 1, which is minus gmm over r. Again, you don't need this for this problem. We intended you to do it by angular momentum, but I've had a lot of students asking, hey, can't I use conservation of energy? Yes, you can, but you need a form for the potential energy of gravity that applies off of Earth's surface. So people asking about this one. This was last problem, Isabel. So Isabel, are you good on problem 5 now? Whoops, not problem 3, problem 5. Good, Isabel. Okay, we have requests for 1A and for number 3. So let's talk about 1A. 1A says, to what height will the hoop roll up the slope? So 1A asks you to imagine a hoop maybe it's a donut. So somebody rolls a donut up a hoop, or up a slope, and they want to know the height h there. So let's review our chart of how you know what you can use. I'm going to copy it. Give me a moment. I'm going to paste this a couple of other times, so I do want to get this copied. There we go. So, copy. Now I can go down here and paste this on this slide. Sorry, I am new to using a tablet. Paste. There we are. So of these three techniques, we have to choose which one to use. And it turns out that here, we don't have conservation of angular momentum because there is friction as the thing rolls up the slope. There's not a common center about which things rotate. So we do have external torques. Obviously, we have a spinning thing that's going to stop spinning. Rotational kinematics is potentially difficult if the slope is curved. It turns out here what you want to use is the conservation of energy. Now, you might say that there is friction as the hoop rolls up the slope. At the end of class today, I'm going to reassure you that energy is conserved as you go up the slope. Total kinetic plus rotational energy. So you can write down that the rotational initial energy plus the translational initial energy plus the work done by all forces, or equivalently, the initial potential energy, equals the final rotational kinetic energy plus final translational kinetic energy plus the final potential energy. Renji, does that answer your question about... No, Jasmine. Jasmine asked about 1A. Does this answer your question about how to do that? Okay. Renji wants to do number 3. No, I don't want to add a bookmark. To add a page. So here we have a bar. It initially starts horizontal. It's a thick bar. And then it rotates to vertical. There are 2 blobs on the end. I think the big blob was over here, yeah. There's a big blob there, there's a little blob here. And then when you let go of it, it's going to rotate. Like so. Now, again, we've got our checklist for which methods we can use. So in this case, is it possible to do it by saying that the torque required to setting its initial angular momentum? Okay, so angular momentum is not conserved here. And that's kind of a gotcha. A bunch of students have said, oh, let's do this with angular momentum. But there are external torques. Gravity here applies an external torque. So this thing is fixed to rotate around its center, right? But, you know, gravity pulls it this way. There's only a small force of gravity on that side. So, oh, Taj, I'm sorry. Is it possible to do it by saying the torque required to blah, blah? Let me see. Yeah, so this problem is super hard. Like number 1 is you can't really do it with angular momentum because as it rolls up the slope, there is friction. You know, if you imagine that the slope was covered in butter, then it would just slide up the slope rather than rolling. So actually friction, static friction, is required to make this thing roll without slipping. And that means that you can't use conservation of angular momentum because friction applies a torque to it. Could I please? Yes, Grace. I'm sorry. I didn't want to ignore Taj's comment about the previous question. I want to make sure that all the students' questions and comments get answered. So yes, Grace, we can certainly continue this one. So I can't use angular momentum, and the angular acceleration is not going to be constant here, right? Because as the thing rotates, the torque is going to change. So do I have all of the things that I need to use conservation of energy? Well, I've got clear before and after pictures, and I can account by for the work done by all the forces, right? It's basically gravity, and I know how to write down a form for gravitational potential energy. So energy approaches to this problem are the right ones to use. Now here you have 3 things that move, right? Because this thing, that's got a mass. The rod has a mass 3 times the little one, and the big one has a mass of 2 times the little one. So you need to think about the kinetic energy of all 3 of those, because in this final state, right, this thing is moving this way, that thing is moving that way, and the bar is rotating. There are a couple of different ways to do it, but you've got to think about all of their motion when you're accounting for the final kinetic energy. Does that clarify this problem, Grace? And Renji, who asked about this? Could I go over question 3 from last Friday's recitation? I could, but I want to give people one more chance to make sure we're clear here. So actually, why don't you type any more questions if you've got them from last Friday's recitation? Um, so I'm not going to do the full solution because the full solution I'm going to record and put up on video. Yeah, Nathaniel, please ask about it. Like it's certainly okay to ask about it here, um, but in the interest of time, since I'm going to record a full solution, I'm just going to like talk about how to approach it. Renji says, so we still consider the mass of the stick here? Yes, because as the stick spins, it's going to have some kinetic energy. You might imagine that if I had a stick made out of uranium, something very, very heavy, it wouldn't rotate as fast as if I had a stick made out of something very light. Dante, so you say for this problem you can't use net torque and use the angular acceleration value. You could, but this problem asks you to find the speed at the bottom, the angular velocity, I think. So it's what is omega here? And the problem is, in order to relate angular acceleration to omega, right, you have omega final equals omega initial plus alpha t, and this is valid only if alpha is a constant. And in this problem, alpha is not going to be constant because as the thing turns, as its angle starts to change, the torque will be different. So yes, you can use net torque and calculate the angular acceleration at any point in time, but then relating that angular acceleration will always be changing. And relating that to the velocity at the end actually will require some difficult calculus. So remember for Renji, for rotational kinetic energy, so this is translational kinetic energy, and 1/2 I omega squared is rotational kinetic energy, because mass is like moment of inertia, and velocity is like angular velocity. Isabella, I don't want to write the equation here because then it's just one line of algebra. Um, so I'd like you to ponder that. I mean, it's just conservation of energy. Poke me on Discord or in the physics clinic today if you want help. The moment of inertia for a rod around its center is 1/12 ml squared. That's in the table. Okay, so Nathaniel, let me just speak quickly about how to do question 3 from last Friday's recitation. So basically you have a spinning rod with 2 beads that can slide back and forth on it. That's very similar to the ice skater problem, right? You have a rotating object that changes its moment of inertia. And as it changes its moment of inertia, its angular velocity changes. So problem 3 from last Friday's recitation is conservation of angular momentum. And I'll do the full solution on video as soon as I get to record it. I do unfortunately want to move on because there's something at the end of class today that you'll need for next week's homework, and I want to make absolutely sure that we get that done. So let me move on. So here is a problem, and this is why I wanted to move on. I got a lot of comments from students saying that they were unclear on stuff from yesterday or from Tuesday, and they'd like to review it. So here's a problem that kind of concerns the topics from last Tuesday's or from Tuesday's lecture. Would you all like to do this problem as an example? Okay. A couple people say yes, so let's do it. How are we going to do this problem? Y'all tell me. What approach do we take? Well, so conservation of energy. The trouble there is to use conservation of energy, you need clear before and after states, right? You need to say, all right, the energy in picture 1 is the same as the energy in picture 2. But we've only got one picture here. So I can't use conservation of energy. I need something else. What other thing can I use? Torque. So I can calculate the sum of the torques. And what does that have to equal here? We know that that's I alpha, but do I know anything about I or alpha for this system? Well, is this thing moving? Let's start there. No, it's not moving. Alpha is 0. So I know in this problem, this is what's called a static equilibrium problem. So if something is not moving, then both the sum of the forces is 0 and the sum of the torques is 0. It turns out that its moment of inertia is not super interesting. Yes, you're right, Jacob. We do know its moment of inertia. It's just 1/12 ml squared. But it turns out it doesn't matter, because no matter what its moment of inertia is, that's multiplied by 0 here. So what we'll do here is we will draw an extended free body diagram, which is a free body diagram where you label both what the forces are and where they act. And then, how did I know it's equal to 0? So alpha, oh, wrong tool. Alpha is the angular acceleration, right? And if this rod had an angular acceleration, then that means that its angular velocity would be changing, and it would either fall down and hit the ground or fly up into the air and hit the building. So the whole point here is the reason we have attached a cable to it is to hold it in place. So we know that's 0 because the thing doesn't move. The whole point of the engineering reason for the cable is to keep the thing from moving. So here's our strategy. So remember, an extended free body diagram, you draw all the forces where they act. So let's draw those forces. There are 4 of them. I'm actually going to scroll down. We'll use that table later. I just want to do it all on one page. Tell me what the 4 forces are and where they act. Okay, gravity of which thing? Because we've got both the rod and the sign. Okay, so the gravity down of the sign, that acts where the sign is. Right, so we have this one. So the mass of the sign is little m, so that's mg. Where does the gravity of the rod act? Yeah, Derek, we'll get to the trig in a minute. You're a bit ahead of us, which is fine. Yeah, so the gravity of the rod acts at its center. Wrong tool. Want my little arrow drawing thing. Blurp. There are two other forces. What are those? Tension. So that acts where the rope is. There's one more. What's that? Would there be friction on the ground? So it's not attached to the ground, it's attached to the side of a building, but yes. So this is attached with a hinge. Over here it's like screwed into the building so it can pivot. And there's some other force here at the hinge pointing in some direction that we don't know. Yes, Adam, so you can, it's kind of equal either way. You can either say the sign applies a tension to the rod, or you can say, oh, yeah, if it's static, that tension is just the weight of the sign. So this is really the tension from the weight of the sign. So we've got four forces. The hinge with magnitude FH, the weight of the rod, which has weight, magnitude mg, the tension from the sign, which has magnitude little mg, and then the cable tension, which is magnitude T, and that is our unknown. That's what we want to try to find. So here, I'm going to need to calculate the torque applied by all of these. But remember, torque is around a particular pivot. And when you're choosing the location of the pivot, it's always a good idea to think if there are any forces that you don't know about, that you don't care about, and you don't want to think about. So do we have any forces in our problem that we don't like? We don't know them, we don't care about them, we don't want to find them. The hinge, yeah, I don't want to worry about that. I don't even know which direction it goes in. So I'm going to choose this location to be my pivot point. I usually mark it with a circle with an X through it. And then that means that the radius from the, remember the radius here, like when I say radius, this is the distance from the pivot to the force. So for the hinge, that is 0. The sine of the angle between them, again, to clarify, this is the angle between the radius vector from the pivot to point where the force acts and the force, right? But the radius vector is 0, so there's a mathematical symbol for the sine of that angle, which kind of looks like that, right? I don't know. The point is that the torque applied by the hinge is 0. That's why we chose our pivot there. So now let's do all of the others. What is the radius between the hinge and the place where the weight of the rod acts? So I want to fill in that blank. Careful, it's not 1 meter. It's the radius vector here. Let me get that arrow out of the way because we don't care about it. The radius vector here is that one. So how long is that? It's 2 meters. Yeah, it's half the length. So the radius vector here is, whoop, wrong tool, is 2 meters, which is L over 2. What's the sine of the angle between the radius and the force? What is that angle? 30. Yeah, it's not 60. All of you saying 30 are right. It is this angle right here, the one between the radius vector and the force vector. So here theta equals 30 degrees. So the sine of the angle here is sine 30 degrees. Now, using the convention where counterclockwise is positive, does this force apply a positive or negative torque? Negative, right, Grace? Because that makes it go clockwise. So the torque here then is just the product of all of those things. It is sorry, I'm at the edge of my tablet and it's difficult to write neatly here. It is L over 2 mg sine 30 degrees. Okay, let's do the rest. Can it also be 150 degrees for the angle because of 60 plus 90, which is the same as sine 30 in the calculator? Yes. And well, it's actually not quite the same, Tammy, because the sine of 150 degrees is negative. So there are some students who like to think about this as like drawing the two vectors. So I know what you're thinking. You're thinking like, let's draw that here, let's draw this here, and then think about the angle like that, which gives you 150 degrees, and also gives you the minus sign. If that makes you happy, you can certainly do that. That breaks my brain for some reason. I'm like, I don't want to do that. But yeah, it could also be 150. That approach is certainly valid. So here, the radius now is, let's see, instead of 2 meters, this is going to be 3 meters, right? Because now if I'm thinking about the sine, that's the radius vector. And if that piece at the end is 1 meter, right, then that means that that length is 3 meters. So this is going to be 3 meters, or 3L over 4, wrong color, The angle will again be 30 degrees. This also applies a negative torque because it's also trying to make this thing go clockwise. And the torque here then will be 3L over 4 big mg sine 30 degrees. Now, let's look at the tension in the cable. So here, its radius is just L. This time, what's the angle? Thinking about the tension in the cable. $60. Yeah. That's 60 degrees. This is the sine of 60. This one's positive, right? Because that makes it turn that way. So the torque here is TL sine 60 degrees. So remember, our strategy here was to figure out what all the torques are, and then to just add all of them up and set them to 0. So I know that the sum of the torques is 0. So that means that 0 plus, minus L over 2 mg sine 30 degrees minus 3L over 4 big mg sine 30 degrees plus TL sine 60 degrees equals 0. Now I can cancel an L from each piece. Did I mess stuff up? Yes, I did. Thank you. Thank you. I flipped my little m and big M. That's easy enough to fix. And then I just solve that equation. Well, it's one line. So, and then when I do the algebra, I get that T is 1/2 big mg sine 30 degrees plus 3/4 little m g sine 30 degrees all over the sine of 60 degrees. Does this clarify the material from Tuesday? This idea of like how you calculate torque. Many students find writing everything out in a little table like this to be very helpful. So if that's something that like clicks for the way that your brain works, then do that. Any more questions about this? I'd like to move on to one more example. Okay. So this is a question about a kitty. This cat, my girlfriend and I at the time adopted this sweet little kitten in 2004. Actually, she found the kitten hanging by his front paws from the staircase by our apartment and put the little kitty in my apartment when I was at work and texted me and said, by the way, you have a cat now. And we named him Loki because he was such a little troublemaker and ankle biter, and he would jump out from behind stuff and claw you, and he was the sweetest, most adorable thing ever. And she's now living in Minnesota and has this kitty who is almost 16 years old now, and he is sick. She texted me last night to say that the sweet little kitty is not doing so well. So I figured the best way to honor our sweet little fuzzball is to put him in a problem. She's now living in Minnesota with her wonderful husband. So, yeah, Kevin, it's sad. Like this little guy was a big part of my college life. Like in 2004, that was my last year in college. So I have fond memories of this little fuzzy. Um, so here's Loki. He knocks a ball of yarn off of a table and then steps on it. So as the ball of yarn goes down off of the table, right, so here's Loki. He'll be a little orange box. Maybe he's got some cat ears and some whiskers. That's our physics cat. And he knocks this ball of yarn off the table. Maybe it's red yarn. And it's hanging from a thread. So as it goes down, it's got to rotate this way. It's going to have an angular acceleration, and it's going to have a translational acceleration, A. So we're going to need both F equals ma and torque equals I alpha to figure out this problem. So let's draw the free body diagram. This is an extended free body diagram, right? Because we have an object that both rotates and translates, so we need to calculate torques. So here it is. What forces act on it? Well, there's only two. Tension over here. And gravity acting at the center. And we'll say that this ball has a radius r. So of these two forces, only one of them causes torque. That's the tension. The torque here is minus TR. It's minus because that's causing it to spin clockwise. So that means that since the thing obeys both F equals ma and torque equals I alpha, I need both of those equations. I'm going to get a system of equations that relates together its translation and its rotation. So I know torque equals I alpha. Putting in the things there, because there's only one force that causes a torque, that means that minus TR equals, so I'm going to put in the moment of inertia now, is 2/5 mr squared alpha. And then for Newton's second law, the sum of the forces equals ma. So, well, I've got two forces. T minus mg equals ma. Now, this may look like three equations and two unknowns. I want to take these two equations. I'm going to put them on the next page. So we're going to do this problem as a two-pager. So what did we wind up with? Let's copy the free body diagram here. So we need you again. Actually, we need all of you. So we'll stick you there. We'll make you a little bit smaller. So we've got these two equations, but they contain both the angular acceleration and the linear acceleration. Remember, the thing both turns here and it falls. So what's the relation between A and alpha? Yes. So Dante says that, I'm going to write it this way, A equals alpha r, which is equivalent to what you said. But this is just true for the magnitude. It's actually plus or minus alpha r. And we need to think carefully about whether it's plus or minus. So looking at our picture, is alpha positive or negative? Keeping in mind the convention that counterclockwise is positive. Alpha's negative. Is A positive or negative? We'll use the conventional coordinate system everyone likes there. A's negative because the thing accelerates downward. So A equals plus alpha r, since A and alpha have the same sign. So now that we know that, yeah, no worries, Derek. I mean, again, this is different depending on the coordinate system you pick. It's different depending on whether Loki knocks the ball off of the left or the right-hand side of the table. So here, the fact that it came out positive here is just specific to the way we set up this problem, the way I set up this problem. You might do it in a different way. I just had to pick something in order to do it on the slides, So when would the r be negative? So suppose, you might pick a different coordinate system, or maybe the string was on the other side of the ball, right? Maybe you have something like this, right? And in that case, it would be rotating that way. So in that case, alpha would be positive, A would be negative, and A would be minus alpha r. Does that answer your question, Griffin? Okay, good. So now let's do a bit of algebra. I'm about to show you a pattern that recurs quite often, so you'll need this pattern again. So let's look at now this equation. So I have minus TR equals 2/5 mr squared alpha. Now, the answer doesn't depend on the radius, and both of these r's will go away in a particular way. And this is a pattern you all should be familiar with. I can cancel one of the r's right away. That gives me minus t equals 2/5 m, and I'm going to write this in color, r alpha. Do we know anything about what r alpha is? Yeah, we just figured out that that's A. So that becomes T equals minus 2/5 MA. And now, yes, exactly, Deanna. And now I can substitute that in here. So if I substitute that into the other equation, that gives me minus 2/5 MA. That came from rotation. And you recognize the 2/5 here as part of the moment of inertia. Minus mg equals ma. And doing the algebra gives us a equals 5/7 g. And this makes sense. The rate that it falls is a little bit slower than free fall because the tension in the string slows it down. So this is what we expect. Are there any questions about this problem? How we did what we just did here, and how this works where you have an object that both translates and rotates? There will be one or two of these on the homework, and there'll also be one on the final. So make sure you understand this. Where did the m come from in between the 2/5 a? So this m here, Matthew? Yeah. So the 2/5 mr squared is the moment of inertia, right? So remember, the net torque is I alpha, so we just took this moment of inertia and stuck it there. Oh, yeah, I dropped a minus sign. You're right, it goes down. Thank you, Derek. Thank you. I rely on students to fix my minus signs. Okay, I've got one more thing I'd like to talk about, and that is how work applies to this problem. Why did MRA become MA? This is MR alpha, and we observed that R alpha equals A. So MR alpha equals MA. Does that answer your question, Renji? Good, good. All right, we got one more thing to talk about. I want to kind of relate this back to the work energy theorem. So it turns out there is a work energy theorem for rotation as well. The work energy theorem says that work is change in kinetic energy, right? So the rotational equivalent to mass is moment of inertia. The rotational equivalent to velocity is angular velocity. The rotational equivalent to force is torque. And the rotational equivalent to displacement is a change in angle. So it shouldn't surprise us then that the rotational work energy theorem has that form. I'm going to skip a bunch of slides here. There are tons of questions early, so there's one more kind of example and thing to work through that we're not going to do. But this is interesting because this lets you calculate the work done by a torque. And yeah, we're going to skip that. Like these slides were here, like I knew I would only get to them if you all just didn't have any homework questions, so I had spare stuff ready to do. So remember that translational work is force times displacement. And when we took derivatives of that, translational power is force times velocity. And remember that homework set you did about a bicycle? we can do the same thing with rotation. So rotational work is torque times change in angle. So that means that rotational power is torque times angular velocity. Do we have any people here in the audience or in the class who like sports cars, high performance cars, who like to drive very fast? I have a old car with a tiny little engine, so I'm not one of them. Martin likes to go fast. All right. So I'm sure you have seen things that are torque and power curves for engines, right? That tell you that a motor in a car can produce a certain amount of torque at different angular velocities, and that's related to the amount of power it can produce. You have a question actually on your next homework set about transmissions, why machines like cars and bicycles and so on use transmissions with gears. But what this is telling us is that there's a relation between the power that an engine supplies and both the torque that it's applying to its drive shaft and the rate at which the drive shaft turns. So the mechanical engineers think about this sort of thing pretty frequently. We have 2 minutes left. Are there any questions that people would like to ask in our remaining 2 minutes? Okay, I have a favor to ask you all. So Tuesday's class is going to be a review in part. It's going to be like, what have we done? What's all the ground we've covered? And I would like you all to go back over the semester, think about all the stuff you've done, maybe look at your past exams, your past homeworks, and find stuff you didn't understand at the time, because we want to make sure that you do get this and get all of those questions right, because we want you to ace the final. So look back over the semester, find the stuff that you'd like to talk about on Tuesday, and show up on Tuesday with your questions in mind. We'll also be doing all those review sessions next week where I can also answer your questions. Otherwise, you all have a wonderful day. I'm going to hang around for just a few minutes to answer any more questions. But otherwise, I have another class to teach at 12:30, so I'll hang around until 12, maybe 24, and then I'll get ready for my next class. So thank you all.